Hello, my name is Darcy Wilson, and today I'll be talking to you about plastic and elastic deformation. Stress is a measure of force applied of an object's cross-sectional area. The object will respond in a change in length known as strain. Strain is the change of a material's length either through tension, pulling, or compression, which is squishing. It is defined as the extension per unit of length. Tension is the twisting motion of an object as a result of an applied torque. Tension is measured in Newton meters. Shear stress is generated in the act of torsion and occurs in pairs to maintain equilibrium, parallel to the material surface. It is a result of parts of an object trying to slip past each other. We call the deformation created by shear stress shear strain. It is defined as the change in an angle of the element. The same formula is used as in typical strain. However, we measure deformation perpendicularly to a given line rather than parallel. Poisson ratio is a measure of the Poisson's effect, which can be described as when a material is compressed in one direction, it usually tends to expand in the other two directions, perpendicular to the direction of the compression. The Poisson ratio is the fraction of expansion divided by the fraction of compression for small values of these changes. Poisson ratio for a list of materials is shown to the left. Note that Poisson ratio has to be between the ranges of -1 and 0.5. Young's modulus, also known as tensile modulus or elastic modulus, is the measure of the stiffness of an elastic material. It is equal to stress over strain and is measured in pascals. This table shows the values of Young's modulus for various materials. The concept of strain leads us into the areas of elastic and plastic deformation, where deformation is the change of a shape or size of an object due to an applied force. As deformation occurs, internal intermolecular forces arise that oppose the applied force. If the applied force is not too large, these forces may be sufficient to completely resist the applied force, allowing the object to assume a new equilibrium state and to return to its original state when the load is removed. Elastic deformation is reversible. Once the forces are no longer applied, the object returns to its original shape. Materials such as elastomers and rubbers have high elastic deformation ranges, which means they are able to experience significantly more strain before elongation becomes permanent. However, normal metals, ceramics, and most crystals show linear elasticity and a smaller elastic range, where sigma is the applied stress, E is Young's modulus, and epsilon is the resulting strain. This relationship only applies in the elastic range. The elastic range ends when the material reaches its yield strength, and at this point, plastic deformation begins. The following is a stress versus strain diagram depicting the elasticity phase duration, which leads into the plastic deformation phase, which eventually results in a fracture when strain starts increasing much more rapidly than stress. This type of deformation is irreversible. However, an object in the plastic deformation range will first have undergone elastic deformation, which is reversible. Soft thermoplastics have a rather large plastic deformation range, as do ductile metals. Hard thermosetting plastics, rubber, crystals, and ceramics have minimal plastic deformation ranges. Under tensile stress, plastic deformation is characterized by a strain hardening region and a necking region, and finally a fracture. The necking phase is called so because the cross-sectional area of the object decreases. During necking, the material can no longer withstand the maximum stress and the strain in the specimen rapidly increases. When a single crystal is deformed under a tensile stress, it is observed that plastic deformation occurs by slipped on well-defined parallel crystal planes. Sections of the crystal slide relative to one another, changing the geometry of the sample as shown in the diagram. If the top half of the crystal is slipping one plane at a time, then only a small fraction of the bonds are broken at any given time, and this would require a small force. The propagation of one dislocation across the plane causes the top half of the crystal to move or slip with respect to the bottom half, but we do not have to break all the bonds across the middle plane simultaneously, which would require a very large force. For mixed dislocations, direction of motion is in between parallel and perpendicular to the applied shear stress. In single crystals, there are preferred planes where dislocations move, slip planes. Within the slip planes, there are preferred directions for dislocation movement, slip directions. The set of slip planes and directions constitute slip systems. Superplasticity is the phenomenon of extraordinarily ductility exhibited by some alloys with extremely fine grain size, when deformed at elevated temperatures and in certain ranges of strain rate. Superplastic materials are deformed well beyond its usual breaking point, usually over about 200% during tensile deformation.